Okay, today's day one for section 4.6, and we're going to start off with mindset here. How does this fit in with what we've been working on? Section 4.6 is just an extension of 4.5, use substitution. We will be using the same use substitution techniques in 4.6 as we did in 4.5, but we'll be doing so focusing on a natural logarithm, or ln of x. So key facts we need to remember: if we take the derivative of the natural log of x, that's 1 over x, and then the antiderivative, or the integral of that, the integral of 1 over x is ln of x plus our constant of integration. And to avoid any domain issues, very often that x is put inside of absolute value bars. All right, as far as the overall skill set, there's really not a whole lot new to talk about. It's just, let's do the same thing we did in 4.5, except for the focus is going to be on things that involve these guys right here. So what I'm going to do is run through these examples. So, focus that. Alright, so starting off pretty basic here. For example 1, we want to integrate 7 over x with respect to x. Well, one strategy we've been using for quite a while, it seems, is it's very advantageous very often to get the the constant rather, to the outside. So if we rewrite that as 7 times the integral of 1 over x, that, oops, where are we at here? Make this a little bit bigger to match. That now lines up with this perfectly. So the constant's just coming along for the ride. That integrates to this. And then usually we always check to see, well, can that be simplified or made look better than it is, more convenient? In that case, there's not a whole lot else we could do with it. Alright, variation. What if, instead of that 7 being on the top of the fraction, what if it's the coefficient of x on the bottom? This is where the u substitution kicks in. If we let u be the 7x, that makes du 7dx. And the same as we did in section 4.5, very often we want to divide that over here. So that gets us to 1/7 du is equal to dx. Alright, now on to the substitution step. So the 1 over 7x is going to be replaced by 1 over u, because 7x is u by our substitution. Okay, that dx gets replaced by 1/7 du. Same as we did in section 4.5, it's more convenient to put that 1/7 on the outside and a du there. So now this here matches that right here. So we can do that integration. The 1/7 coming along for the ride. This integrates to that. And then the same as we did in section 4.5, after we get that answer in terms of u, substitute back in again to get our final answer. Check to see whether that needs to be cleaned up at all. That's pretty good. There's not a whole lot else we need to do with that. Alright, moving up the food chain a little bit in terms of more stuff to be looking at. One of the general strategies that we looked for when we're using use substitution is if we took the derivative of some part of what we're trying to integrate, does it equal to some other part? So specifically to this problem, if we look at the denominator, x squared minus 5x, if we take that derivative, it gives us the 2x minus 5. So we want to make that our u. So if u is x squared minus 5, x squared minus 5x, du is 2x minus 5 dx. Now, when we do the substitution, that x squared minus 5x is the u that's on the bottom. This right here gets replaced with du. Now, what we're trying to integrate matches that as is, do the integration, substitute back in order to get our final answer. All right, now, similar to what we saw in section 4.5, sometimes the constants don't quite line up when we do this, but we can adjust for it. So, for example, 4, I'm going to take that 2, put it to the outside, because very often that is advantageous to do. If we let u be 5x minus 3, which is the denominator, that makes du 5dx. Divide both sides by 5. And then we do the substitution step. So, comparing this to this, 1 over 5x minus 3 becomes 1 over u. The dx gets replaced with 1/5 du. We put the 1/5 on the outside. We still got that 2 out there from the previous move that we did, du. This integrates to natural log, clean up the constant in front, substitute back in, and that gets us to our final answer. All right, another thing that we saw in section 4.5 was that in order to get the constants to line up, sometimes you need to do a little bit of factoring. So, a common theme for examples 2, 3, and 4 was u was the denominator of the fraction. So if we stick with that as our thought process, and we make u be 2x to the third minus 9x, that makes du 6x squared minus 9. Now 6x squared minus 9 doesn't quite match the 2x squared minus 3 up top, but if we factor out a 3, then it does. So that's kind of the trick, or not necessarily the trick, but the strategy in order to make this work. We're going to get this over there, divide both sides by 3, as we've done with many of these problems, and now we can do the substitution. So the bottom of the fraction, the 2x to the third minus 9x, that gets replaced with u. 2x squared minus 3 dx gets replaced with 1/3 du. We like to put the 1/3 on the outside. That's where the du is. This integrates to natural log. Substitute back in order to get the final answer. So, zoom back out to everything here for a little recap. This first one is just a very minor variation on integrating 1 over x as is. Just kind of a quick little warm-up, something we probably already addressed and knew how to do prior to this lesson. For examples 2, 3, 4, and 5, the overall strategy was we let u equal the bottom of the fraction, and then with u being the bottom of the fraction, it came down to integrating at some point 1 over u du, 1 over u du, 1 over u du. So that is kind of one common type of problem in terms of lumping this into a big category, is letting that u be the bottom of the fraction. All right, some other things that can happen. Let me zoom back in here on number 6 a little bit. Right, now, if we just let u be the bottom of the fraction as is, when we find du dx, we'd end up having to do a product rule, and it would get rather messy and wouldn't really lead anywhere. So, going back to the bigger picture of u substitution, if we take the derivative of something that's in that problem, does it produce something else that's in that problem? So what I mean by that is if we take the derivative of ln of x, it gives us 1 over x. So that's our clue. That's a strategy that we should consider. So if we let u be ln of x, du is 1 over x dx. So when we do our substitution, 1 over ln of x is going to be 1 over u. And then that x dx gets replaced with du. So that gives us this guy to integrate, and then from there we substitute back in and we get our final answer. Alright, 7 is a slightly bigger version of 6. If we let u be the entire denominator, du dx would be rather messy, and it really wouldn't lead to anything that would help us get this thing integrated. The best move here is we let u be this part of the denominator right there, just like we let u be that part of the denominator right there. So I'm going to take that 4, put it to the outside. Usually that tends to work better to get that constant to the outside. U is going to be y1 plus ln of 2x. Now when we take the derivative of a constant is just 0. And then we got a little bit of a chain rule here. 1 over 2x times 2, which simplifies down to just 1 over x. So now when we do our substitution, that 4 is already to the outside. So we're left with the 1 up top. 1 plus ln of 2x, that's the u on the bottom. And then this x dx here gets replaced with the du. Integrate, substitute back in, gets us to the final answer. Lift this up a little bit there. All right, last example for today, number 8. Now keep in mind as a general strategy that you always have in pretty much anything we do in calculus. Something to consider in terms of rewriting an expression is if you have multiple terms on top and a single term on the bottom. If you split that up into separate fractions, very often dealing with those smaller individual fractions will make the problem easier to deal with. So in this particular case, let's see how that plays out. So we have 3x to the third, put that over x, 1 over x. Because technically this should be in either parentheses or brackets. Okay, 3x squared, 3x to the third over x reduces to 3x squared. 1 over x we're not going to do anything with. And now for the first part of the integral, that's just regular power rule. That is the same logarithm we've been using all along. Clean that up a little bit, and we can bypass the entire u substitution. So what looks like it could be a u substitution problem, it's not necessary. If we just rewrite that original expression a little bit before we get to the integration step, we don't necessarily have to do u substitution for this. Much cleaner, much faster to approach it that way.